Welcome back to another episode of Tech Talk, where we dive deep into the world of technology and software engineering. Today, we're focusing on two critical concepts: reliability and scalability in software systems. As technology continues to evolve, the need for systems that can withstand failures and handle increased loads becomes more important than ever. So, grab your headphones and let's explore how we can build robust software systems that not only function well, but also adapt to growing demands. Let's kick things off with reliability. This isn't just a buzzword for mission-critical systems like air traffic control or nuclear power plants. It's essential for all applications, even those that might seem mundane at first glance. For example, think about a parent relying on a photo application to store precious memories. If that system fails, the emotional and financial repercussions can be significant. To enhance reliability, we can use software fault tolerance techniques along with hardware redundancy. This combination allows systems to stay operational even when individual components fail. For instance, a single server system typically requires planned downtime for maintenance. In contrast, a fault-tolerant system can be patched one node at a time, enabling rolling upgrades without disrupting service. Now, let's talk about the different types of faults we might encounter. Hardware faults can be concerning, but they often don't correlate across systems. If one machine's disk fails, it doesn't necessarily mean another will fail at the same time, unless there's a common cause, like overheating. Systematic errors, however, present a different challenge. These errors can be harder to predict and often lead to widespread failures across multiple nodes. For example, consider a software bug that causes an application server to crash when it encounters a specific input. A notable instance of this occurred during the leap second on June 30th, 2012. When many applications hung due to a bug in the Linux kernel. Other examples include runaway processes that consume shared resources or cascading failures where one component's fault triggers another's. Systematic faults often arise from incorrect assumptions made by software about its environment. While these assumptions may hold true most of the time, they can lead to failures under unusual circumstances. So, how do we mitigate these risks? There's no one-size-fits-all solution, but several strategies can help. First, we need to thoroughly analyze our system's assumptions and interactions. Rigorous testing is essential, ranging from unit tests to full system integration tests. Automated testing can be particularly effective in identifying corner cases that might not surface during normal operations. It's also important to recognize that human error plays a significant role in system reliability. Studies show that configuration errors by operators are a leading cause of outages, often more so than hardware failures. To counteract this, we can design systems that minimize opportunities for error. This includes creating intuitive interfaces and providing sandbox environments for experimentation without affecting live users. Quick recovery from human errors is vital as well. Implementing features that allow for easy rollbacks of configuration changes or gradual code rollouts can significantly reduce the impact of mistakes. Plus, detailed monitoring of system performance and error rates, often referred to as telemetry, can provide early warning signals and help diagnose issues when they arise. Now let's shift our focus to scalability. As systems grow, they must be able to handle increased loads. And scalability isn't a one-size-fits-all concept. It's about understanding how a system can adapt as demands change. For instance, if a service grows from 10,000 concurrent users to 100,000, we need to think about how to manage that growth effectively. To discuss scalability, we first need to define the current load on the system using load parameters. These can vary based on the architecture of the system. For example, in a web service, load parameters might include requests per second or the ratio of reads to writes in a database. Let's look at Twitter as a case study. In November 2012, Twitter faced the challenge of handling a significant volume of requests. Users were publishing tweets at an average rate of 4,600 requests per second, peaking at over 12,000. However, the real challenge lay in the fan-out effect. Each tweet needed to be delivered to multiple followers, resulting in a massive number of writes to the home timeline caches. To manage this, Twitter employed two strategies. They could either insert tweets into a global collection or maintain a cache for each user's home timeline. The latter proved more efficient as it allowed for quicker reads by pre-computing results. However, this approach also required handling the increased write load, particularly for users with a large number of followers. Interestingly, Twitter eventually adopted a hybrid model. While most tweets were still fanned out to home timelines upon posting, tweets from high-profile users were fetched separately when a user accessed their timeline. This strategy effectively balanced the load, ensuring consistent performance. So, what can we learn from Twitter's approach? Scalability discussions should focus on understanding the unique characteristics of your application. By analyzing load parameters and considering how they interact with user behavior, we can develop strategies that allow our systems to grow seamlessly. In conclusion, building reliable and scalable software systems is a multifaceted challenge that requires a blend of strategies. From employing fault-tolerance techniques and rigorous testing to designing for human error and understanding load parameters, each element plays a crucial role in ensuring that our systems can withstand failures and adapt to growth. As technology continues to evolve, the importance of reliability and scalability will only increase. By prioritizing these principles in our development practices, we can create software that not only meets today's demands, but is also prepared for the challenges of tomorrow. Thanks for tuning in to this episode of Tech Talk. If you enjoyed our discussion, don't forget to subscribe and share with your fellow tech enthusiasts. Until next time, keep innovating and building resilient systems.